So, have you guys looked at the study guide?
Yeah.
Of course not. I just got that on recording, so it's kind of exposed now. Okay, so basically it's just on sections 1 and 2, so elimination reactions and some electrophilic addition reactions. So I basically just compiled a few examples of things you might see on the test. For this first section, just what to keep in mind. It's regiochemistry, stereochemistry of E1 and E2 reactions. E1, the regiochemistry is determined by the intermediate carbocation, the stability of the carbocation. Same for stereochemistry. For E2, regiochemistry is determined by stability of the product and the bulkiness of the base. And stereochemistry is determined by the structure of the substrate. So keep that in mind. That will be very important on this test. And like I said, you may have multiple choice on this one. I don't know if he's changed it or not. If there is multiple choice, study that one homework question that was like the pick E1, E2, SN1, SN2 questions. Study that because they'll be kind of similar to that. Okay, so mechanism for this reaction. So this is secondary substrate, right? And you're given, so most of the questions on the test will be given E1 or E2, because like I said before, it's kind of more difficult to figure out which one is which, rather than SN1 and SN2. So we have T-butoxide, which is a bulky base, E2 reaction, okay? So if I have a bulky base, it's going to be under kinetic control, which is a Hoffman reaction, which is going to mean my less stable product is major. Okay. So I have my substrate. This is my leaving group. My leaving group is going to leave. And then I have my base come in. So there's a hydrogen here that I could take, or there's a hydrogen here I could take. Both of these are beta carbons. Okay. So I have a bulky base, which means a less stable product is going to be a major one. So the less stable product would be formed if I took this hydrogen. Okay. If I formed a double bond here, that would be more stable because it would have less hydrogen around the double bond. But because I have a bulky base, it can't get in here very easily because this is in the way, this is in the way. It can't get in there very easily. This is going to be stereochemical. So because I have a bulky base, it's going to come and take this hydrogen instead. That CH bond is going to break, and those bonding electrons will go to form a double bond there. That is my product.
And that's the entire mechanism. What's the little dot?
That's not. That's just a dot.
Okay, I was like,
Pay no attention to the dot.
No, that's what I'm saying. Last semester we used to have that.
I'm sorry. Okay.
I never know, do you?
That makes sense? All good? Okay. So then we have E1, secondary substrate. Okay, and then hydroxide is my base. So E1 is stepwise, so the leaving group is going to come off first. So that carbon-chlorine bond will break. Chlorine will come off. And I form a carbocation on that middle carbon there. Okay, so you will definitely have rearrangement on this test at some point, so you have to pay attention here. So anytime you make a carbocation, think about if there's a way to make a more stable one. So this is secondary. Okay, is there a way I can make a tertiary?
Yeah.
Yes. So there's a hydrogen here. If I switch that hydrogen to the carbon with the positive charge, that'll switch the positive charge to that tertiary carbon.
It's just a shift.
Yeah. Okay, so now I have that positive charge on the tertiary carbon. Now this is a tertiary carbocation, which is more stable. And that hydrogen switched to this one. Okay. So now base can come in. So I could either take one of those hydrogens or the one I just switched over there. If I take the one I just switched over there, it'll put the double bond in the middle here, and that would be more stable than if I had the double bond here, because I'll have less hydrogen around this one. So my base will come in, take this hydrogen, that CH bond will break, go to form a CC double bond there, which will neutralize that positive charge. Any questions? Makes sense? Okay. So now we have E2 again. The base is non-bulky. Okay, so remember the stipulation for E2, that hydrogen, the beta hydrogen, and the leaving group have to be anticoplanar to have E2. So right now, this is not anticoplanar. So I have the bromine in the plane, that's fine, but I need this hydrogen that's in the back right now, I need that in the plane here. So we're going to rotate. Now I'm going to do the thing I told you last time, which you don't have to do this and you don't have to write this, but I think it's easier to visualize. So if we're just looking at this carbon here in a Newman projection, so I have methyl group up in the plane, and I have ethyl group in the front, hydrogen in the back. So this is the front, this is the back, and this is the plane. Okay, so I want this hydrogen here in the plane. So if from, this is a circle, I have 3 spokes on the circle. From here to here is 120 degrees. So if I want this here, it would just be 60 degrees. But be careful because it won't always be 60 degrees. Depends on what you start with. So if I rotate 60 degrees, my hydrogen down in the plane. Okay, the ethyl group stays in the front of the plane, so just shift it up in the front. Okay, and then this methyl group shifts to the back. Why did I just write back? is in the back. Okay, make sense? So to put that back in molecule form, okay, so this is what I started with. Rotated 60 degrees. So this carbon had no change. But this one, so now I have hydrogen down in the plane. Okay, my ethyl group was in the front, just shifted up in the front, but it's still in the front. Hello. Okay. And then my methyl group shifted down and in the back. Does that make sense, how I did that?
So we keep one of the sides the same.
Yeah.
And then we
There was that homework question where you had to rotate both carbons. I don't think he would give you that on a test. For the most part, you'll only have to rotate one. I don't want to say never, but I really don't think you would.
And what's the purpose of rotating them?
Because you want them anticoplanar. So you want this bromine and this hydrogen all in the same plane, so connected by the lines. So I needed to rotate that hydrogen that was in the back into the plane so I could have it like
I
this.
see.
Okay. So now that I have that, now the base can come in and do things. So base will take the hydrogen, and that CH bond will break. And those bonding electrons will go to make the double bond. CBr bond will break. That'll come off. Okay. And that is my product there.
Okay, I can see it. I got something ahead of it.
Sorry. It's hard to write on this. You don't know how hard it is to write on this.
Never apologize to me. I'm nothing. I'm not a chemist.
It's hard.
Is that double bond?
He just
Yes,
said I am
I'll
nothing.
rewrite it.
Well, I don't.
It's a lot of talk from someone that's nothing over there.
I really won't get very.
Okay. My very first study session ever, I swear my writing was just completely illegible. Like, not even close. I don't even think that's better, but.
Looks good to me.
So in this case, the hydrogen in the front had a break off.
Yeah. Yeah. Any questions here? All good? Okay. So now I have an alcohol. Okay. This is secondary again. This is dehydration of alcohols, which can follow E1 or E2, depending on the alcohol. So, first step is to protonate the OH group because I want it to come off, and that is not a good leaving group, so I have to make it a good leaving group. Which I'm going to do from sulfuric acid. The lone pair of electrons from oxygen takes the hydrogen, which will break that bond.
Where's that, with the H and the bond, where's that at?
I better.
Oh,
Yeah.
I thought it was a symbol for heat. So we're gonna line them up.
Sorry.
In the middle of the action.
Look at how thick this thing is, and I'm trying to write it. I'm sorry.
No, I didn't know. Like I said, I'm here, a pure bug on your windshield.
Well, then quit talking. Okay. So now that I've protonated that OH group, now that oxygen has a positive charge, now it's a good leaving group. So that bond will break and that'll come off. Okay. Now I have a carbocation, it's secondary. Can I do something with it? Question mark. I can, right? There's a hydrogen here. I can switch that hydrogen to that carbon there, which would switch that positive charge to the tertiary carbon.
So do we need to put like H arrangement on there?
Yeah, I normally write H shift or rearrangement if it's something else. So now that counter anion from sulfuric acid, I looked this up before I came here this time. I could not remember my last time. So this is a counter anion when you break off that hydrogen there. Okay. Now this is going to take, it can take either of these hydrogens, they're equivalent, so it doesn't matter which one. Okay, which will break that CH bond, form a double bond there, which will neutralize that positive charge. Any questions?
So then would a byproduct be HOSO3H?
So H2SO4 is a catalyst, so that's not a byproduct. Your byproduct would be water that came off there. But so I used sulfuric acid here, and then when I added that hydrogen back here, I just reformed the sulfuric acid.
Oh,
So if you want us to show all, like, with the catalyst, or can we just do like last semester we did, plus H plus?
I would ask him. I don't know
Okay.
at this point. So yeah, I'm inclined to say that you don't have to show that, but I feel like it would maybe be different because this is the elimination chapter, and that better shows elimination. I would probably ask him. See, this way is never wrong, so this is always a safe bet. So the other option is you can also just use you could use H3O plus, which is acid dissolved in water, which here would give you water, which could take the hydrogen, and then you end up with H3O plus again. That's another option you could use, or, which I don't know if you would accept this at this point, or just H plus minus H plus. I would check, honestly, I'm not 100% sure, but this one is never wrong, so that's a safe option. Any other questions? Okay, so second part that's on your test is electrophilic addition of alkenes. So the whole premise of this is your double bond is electron rich, so it's nucleophilic. It can give electrons to something and can react with electrophiles and add an electrophile to the double bond. So this is a big one, just the whole addition of HX, whatever halogen. Remember this follows Markov-Nikov's rule. So Markov-Nikov rule says that when adding H whatever to something, the hydrogen will add to the carbon that already has the most hydrogen, and the other one will add to the other carbon. And this is just based in carbocation stability rules anyway. So if for some reason you can't remember, just remember you're trying to make the most stable carbocation. Okay, so this is electrophilic because bromine is electronegative, so it's going to be partially negatively charged, which would make the hydrogen partially positively charged, so this hydrogen is electrophilic, and the double bond is nucleophilic. So the pi electrons from the double bond will attack hydrogen, which will break this HBr bond. Okay, so the hydrogen will add to whichever of the doubly bonded carbons already had the most hydrogen, which this one here has 2 hydrogens, and the other one didn't have any. So the hydrogen will add to the one on the end, which I'm not going to show because it's a line structure. And then the positive charge will form on the other carbon. Okay. And now that bromine anion is going to attack the carbocation. Make sense? All good? Victoria, all good?
Yeah.
So this one's a little trickier. You have the whole ring thing here. But, okay. So, how you'll set these up is your bromine is going to be perpendicular to the double bond. Okay, so double bond is nucleophilic. It's going to attack this bromine. One of these lone pair of electrons on the bromine is going to come right back and attack one of the double bonded carbons. And then that bromine to bromine bond is going to break. So I broke the double bond, and now both of these carbons are bonded to this bromine. And now this bromine has one too many bonds, so that's a positive charge. And then I have the other bromine anion. Does that make sense thus far? Okay, and this is called brominium. Okay, so this follows anti-addition, which just means that both of those bromines will add to opposite sides of the double bond. And that's because this bromine because you have this whole mess down here, that bromine's not going to want to get in this whole arena of mess. So it's going to come on top where there's nothing there to hinder it. So it'll normally attack whichever one has less things around it. Okay. So when it attacks this carbon-bromine bond will break. So this bond is still intact. So it's going to be this one here. And then this bond formed up here. And both of these are chiral. I didn't show you the structure here, but just keep that in mind when you're doing these problems. Pay attention to stereochemistry. And if you're making a racemic mixture or a meso compound, just pay attention.
Do the bromines have to be on opposite sides of each other? Like that?
Well, see, so here it doesn't really matter because I didn't show you the 3D structure. So this more or less means nothing because it's not in 3D. If it was in 3D, yes, they have to be in opposite sides. This is just showing that they add an opposite sides, but in this structure is more or less meaningless. But yeah, I would always put that because it has to follow anti-addition. Any questions? Okay. So this is same kind of reaction. It's going to follow anti-addition. So if you do run into any of these and they give you line structure, I would probably just put it in structural formula because I think it's easier to do. I don't quite know why I put this in line structure because I know I don't like it in line structure, but oh well. So CbCH2. Okay. So same thing, you'll set it up with the bromine perpendicular to the double bond. The double bond will attack this top bromine, and one of the lone pair of electrons on bromine will come back and attack one of the double bonded carbons, and then this bromine to bromine bond will break. Okay, so now I formed my brominium intermediate, okay, where I have the three-membered ring, and this bromine holds a positive charge because it has one too many bonds. So now it's going to come and attack one of these carbons, break the bond. So I'll end up with, this bond is still intact, which is there. I formed this bond up here. So like I said, this means pretty much nothing. Now that they're on opposite sides here because this isn't the 3D structure. But this is just to show that it's anti-addition, which we know it is, but yeah, just pay attention to, if you're given the 3D structure, what your option would be. Any questions? Okay, so last thing, I know this is pretty new, but this will be on your test. So I'll put it in. So hydroboration is reaction of an alkene with, this is diborane. But what you're really reacting with is just borane, but borane doesn't come like that. It'll only come as diborane. So this kind of addition is anti-Markov-Nikov. Okay, because you're adding, this is somewhat like HX. Okay, but normally with Markov-Nikov, your hydrogen would add to the double bonded carbon that already has most hydrogen. But in this case, this is too bulky to do that. So it's going to be the opposite to prevent steric hindrance. So I have, so this carbon here has less hydrogen than this one, which means it's more sterically hindered because I have this methyl group here. So my hydrogen is going to add to that one. Okay, and then my BH2 will add to this one because there's less in the way here. Does that make sense? So the double bond will attack borane here, and then this BH bond will attack the other carbon. Okay, so hydrogen will add to that one, and then BH2 will add to this one here. And we rarely ever stop here, so we normally always do this step, which you don't even know the mechanism for. But you will be tested on this reaction at least. So when we do this, we never really want this here. When we react with hydrogen peroxide, then we'll replace that BH2 with an OH and give an alcohol, which is almost always what we actually really want. So this is useful because we can get anti-Markov-Nikov products. So we can get an anti-Markov-Nikov alcohol, which we wouldn't be able to do with other reactions. Does that make sense? So this I just wrote there because it added there, but then its line structure, so I just left it out. It's still there, it's just not.
But we don't have to show the BH2 right now.
No, you don't have to show this mechanism. I don't know this mechanism. So it just replaces it with OH. Any other questions? Okay, last thing. Grignard reagents. So okay. So remember in like Chem 1, so the whole basis of, I don't even know why I asked that. So the whole basis of covalent and ionic bonds is electronegativity, right? So this carbon-bromine bond, bromine is more electronegative than carbon. So here, this bromine will be partially negatively charged. The carbon is partially positively charged, which we know that. We know haloalkanes are electrophilic because of that. Okay? So when I react with magnesium, basically all I do is just slip that magnesium in between the carbon and bromine. So now, originally your carbon was partially positively charged because it was connected to bromine, which is more electronegative, it's pulling electrons more. But now it's connected to magnesium, which is less electronegative. So now the carbon is pulling more electrons than the magnesium. So now your carbon is partially negatively charged, and this is partially positively charged. Still a covalent bond, but the polarity is switched in the opposite direction. Does that make sense? Okay. So because this is partially negatively charged, now this is a carbon nucleophile, which we don't have very many carbon nucleophiles. It's pretty much just these, cyanide, and phenols, I think. So we don't have very many of these. So that's why these are very important. So epoxide up here, after I make this is this product. So now if I react with an epoxide, so oxygen down here is more electronegative than both of these carbons. So this oxygen is partially negatively charged. These carbons are partially positively charged. So because this carbon is a nucleophile, it can attack one of these carbons that's electrophilic. So air will come from the carbon-magnesium bond to whichever one of those carbons is less sterically hindered. We're just going to break this carbon-oxygen bond. So this carbon is now connected to this carbon, okay, which is connected to this carbon, which is now only connected to this oxygen because this bond broke. Okay. Okay. And then this magnesium bromide will attach to this oxygen to stabilize that ion. Okay. So this is this carbon here, and this one is this one, this one is this one. That's that oxygen. Okay. So now this is an ionic bond. Okay, because remember, covalent versus ionic is just based on the gaps in electron negativity. So these don't have a big enough gap to be fully ionic. But now that it's connected to oxygen, now there's a big enough gap for this to be an ionic bond. So, but I don't want this, nobody wants this. So what we're going to do is work up, which basically means just wash in water or a dilute acid. And ions dissociate in water, right? So that's basically what's going to happen here. Is your ions are going to come off. That magnesium and bromide is going to come off. And that oxygen will be protonated into an alcohol. Make sense? So you'll have a few questions like these where he'll give you a few steps and ask you for the intermediate products. So prepare yourself for that. Any questions? All good? That is all I have. If you have homework questions, if you started on your homework, I can take those.